Thank you for the introduction. My name is Neethirajan. I'm a PhD student at the Planck Institute for Chemical Physics for Solids. As Ivan mentioned, this is going to be a talk focused a bit more on magnetism, specifically a bit more into magnetic imaging. I'll go a little bit more in depth into, my supervisor, Claire Donnelly, actually mentioned a brief introduction to what I'm going to present today, but I'll be delving a little bit more deeper. So, yeah. So to start off, I would like to first give a general introduction to why we are interested in magnetism. So it ranges, it's very interwoven into our modern society, from applications ranging from data storage, especially with cloud computing and archival systems with magnetic tape still being used, but also an emerging field of data storage and computing is with spintronics, where the use of topological spin textures and spin currents are used for making efficient devices. But also can be used for generation of renewable energies, specifically the use of permanent magnets with dynamos. Last but not least, you can also find them in natural biological systems where migratory birds use the magnetite present in the beaks for navigation using the Earth's magnetic field, but also small bacteria where they use magnetite particles present in them for orienting themselves in the Earth's magnetic field for navigation. So I'm particularly interested in in thick magnetic systems. So I define them as samples being greater than 1 micrometers in size, which may not be thick for most of the people here. But specifically, I would like to highlight 2 systems here that I would like to show in this talk. The first being a continuation, which is like with natural magnetite. So we have some collaborators who in 2008, they actually found some from sediments obtained from the Atlantic Ocean, around like 6 million years old. They were able to identify on GM imaging morphologies of particles of like spindles and like spheres and like bullets, and like check this paper for more examples. And they attribute these structures to be of biological origin, specifically for some giant bacteria maybe, and they name them giant magnetofossils. These particles are magnetic, and most studies of these structures have been with TM imaging, where it required them to section them into thinner pieces, so it's a form of destructive imaging. I'll show you why they're quite hard to image and in the next few slides. The next part I'm interested in is particularly topological textures in 3 dimensions, where the extra space in the extended dimension allows for the formation of complex 3-dimensional magnetic structures such as hopions, helionotons, or block points as well. Our choice, in order to probe such materials in magnetism, we particularly need 3 main 3 criteria that needs to be met. So first, as I mentioned, we need to probe thick samples. So we need to be able to probe some thick samples in the order of micrometers. Second, we need to be able to probe samples of different compositions, so transition metals to rare earths. And then finally, be able to be probed with nanoscale spatial resolution, because a lot of these topological defects, etc., are formed in the nanoscale. So a natural choice for such demanding the need for such demanding probe is we use X-rays, where we ensure nanoscale spatialism while being non-invasive. So imagine a simple experiment where you have X-rays, and then you have a sample, and then you have a detector, where you just measure how much your sample is absorbing X-rays. So we make use of an effect called X-ray magnetic circular dichroism, where magically, when you start using circularly polarized X-rays, your absorption really depends on the way your magnetization is oriented. In a simplistic point of view, you can approximate your magnetization to be a pointer made of arrows up and down. And depending on the helicity of the X-rays, you either excite up spins or down spins. And if you raster scan across your sample, and then you get a beautiful 3-dimensional mapping of the magnetization. So if you follow just the corner here, for example, what's black here would appear white over here. That's due to the different dispersion due to the different domains. The scale body is around 500 nanometers. And so taking the logarithmic difference between them, you get a beautiful XMCD image where the blue domains are pointing towards you, and then the red is pointing away from you. So to understand, and so yeah, with this we get a quantum mapping of the magnetization with nanoscale spatial resolution. So there are 2 main regimes which we can probe magnetism. The first is with soft X-rays, where we have very strong magnetic contrast from transition elements, as well as rare earths. And we can probe a wide range of materials while having nanoscale spatial resolution. However, the technique is very limited to thin materials, on the orders of around 200 to 300 nanometers only. On the other hand, you have hard X-rays where you can probe micrometers worth of material, but you only have very weak magnetic contrast. And most of the materials that exhibit these weak contrasts are only rare earths, so you can only probe rare earths in this regime. If we plot what we can measure, with the thicknesses along the graph, you can see that there's like this gap in between here where there are materials that you cannot probe by either hard X-rays or with soft X-rays. So there's been an inherent gap in our imaging capabilities of magnetic systems. And as I showed you before, a lot of these systems, for example, these giant Neethirajan fossils, lie in this thickness regime, so around like 600 to 1 micrometer in range, as well as other thicker magnetic systems. The question I'd like to answer today is if we can actually combine or have a technique that we can actually probe these materials. To start off with, let's first understand why we're actually limited inherently with soft X-rays. And so to understand this a bit more, we did some spectroscopy on a couple of different multilayers, which is like 100 nanometers thick. All you need to understand is that this is a system that has out-of-planar anisotropy, which means that it can only have spins pointing up and down on the plane. So if we do a spectroscopic experiment where we vary the energy and measure XMCD images. So on the top, you see the XMCD images of the sample, and on the bottom here, the black curve here represents the transmission you see through a sample, and then the red curve here plots the XMCD signal you observe. So this red curve is actually extracted from the domains that you see on the top over here. And inherently, immediately what you see is actually that, okay, away from, so this point, this dip, we typically call it resonance. And away from resonance, you see almost no domains. And then on resonance, you see a strong magnetic contrast. So which means that the XMCD is not really a resonant technique. However, can we actually go beyond the amplitude? Because if we look back at a transmission function of an element, it's a complex one, meaning you have an amplitude as well as the phase. However, detectors, they cannot move in the frequency of light, so you don't usually measure the phase and you only measure the amplitude. So there's a way around this where smart people develop techniques called coherent refractive imaging techniques called holography and tychography, to name a few. These techniques use the coherence properties of the beam, and you measure far field diffraction patterns after eliminating a sample with X-rays. And then with help of reconstruction algorithm, you can get both your amplitude as well as your phase. I won't go into detail with the technique, but if anybody's interested, I'm happy to chat about it. Using this technique, we were able to extract the phase XMCD signal as well as the amplitude XMCD signal. So here on the top in the red, you see the amplitude XMCD signal, and then which is represented by this red curve here. And then again, the blue curve here represents the phase XMCD signal extracted from these images over here. And the black curve here again is the transmission you see through the sample. So yeah, there's a lot going on, but I would like to highlight just a few points here where you see phase in the phase XMCD spectra, you see domains almost across the entire energy spectrum. Particularly, I would like to highlight something in the pre-absorption edge over here, where you do have when you have zero amplitude XMCD signal, you still have a measurable phase signal. And if you see the images, indeed, you still see domains over there. And this prompted us to think that, okay, you still have almost 45% transmission in the pre-absorption edge, and maybe you can use the phase XMCD to image bigger systems. So this is indeed what we did. So we took a test sample, which is a iron gadolinium. For the expert here, it's a multilayer system with also autoplanar anisotropy. So I need to know that it still points towards you and away from you. So our first sample was around 400 nanometers thick sample. So here's the transmission spectrum through. So the yellow curve is when it's non-saturating, or like when there's no zero transmission on resonance because the sample is too thick. The green is for the 4 nanometers thick sample, and you see it's almost zero transmission over there. And so indeed, still, you can still measure at energies where there's still transmission through the sample, and then you see beautiful domains and amplitude as well as the phase. So next, we did it the same for like a 1,000 nanometer thick sample, so 1 micron thick. So you see the transmission to the sample significantly decreases. And in comparison, the phase provides beautiful magnetic domains. Okay, so then we went a bit crazy, and then we went we measured a sample 1,700 nanometers thick, so almost 2 microns in thickness, which is almost an order of magnitude higher than what people typically measure. And so you see there's like a tiny transmission through there, but still we were able to measure beautiful phase XMCD images in the pre-absorption edge. So now that we have a technique that can probe such thick systems, we applied it to, I would like to highlight just 2 results over here quickly. The first being with natural magnetite again. So again, we talked to collaborators, and then we were happy to provide some samples for us to image these particles in. And so that's a scanning transmission electron microscopy image of our test sample. So as you can see, there's like an elongated structure here, which is kind of like a bullet. And then in the center, you have like a Q-block dihedron structure, and then you have a smaller bullet here. Just for reference, this sample over here is like around 600 nanometers thick. This is around like 570 nanometers thick, and then this one's like around 300 to 400 nanometers thick. And so, yeah, so these are morphologies that I was talking about that kind of resemble these magnetic fossils. And again, so on resonance, when we take an image using a conventional technique, this is what you see over here. So on the center, you see mostly noise. The scale over here is 500 nanometers. But when you start using the pre-edge phase imaging technique, you obtain these beautiful vortex-like structures in these samples. And this is actually one of the first times that people were able to look into the magnetic structure of these particles non-invasively. Last but not least, before I conclude, I would like to show you our imaging on chiral helium magnets. So our test sample here was a cobalt zinc manganese chiral helium magnet, which orders around room temperature. Currently at the synchrotron, we're mostly limited to room temperature studies, so we're quite picky with our materials at the moment. So here again, the spins here point to like a helical. This is a schematic representing the helical orientation of the domains. And using a focused ion beam, I patterned like a 900 nanometer thick sample in this fashion. So you have like a confined 400 nanometer thick sample, thick region, and then you have like an unconfined cylindrical, kind of like a 1.4 micrometer thick sample. And again, using our pre-edge technique, first, comparing the amplitude and the phase, you see beautiful domains in the phase compared to the amplitude, where it's much, much noisier. And secondly, well, what you would notice is that on the top region, the narrow confined region here, you see the formation of these nice ordered helices, and the contrast is really strong. Whereas in the unconfined region down here, there's much more complex three-dimensional ordering that we still are trying to understand a bit further. And I think we can't really tell, to be honest, I don't think we can tell much from the 3D projection. I think an extension of this technique to 3D would give a much more informed decision of what's actually going on inside, which is actually currently also what we're working on. So before I conclude, I would like to acknowledge the people who are responsible for the great work, specifically my supervisor, Dr. Claire Donnelly, and our group Spin3D. Most of the measurements were performed all of the measurements were performed at Diamond Light Source, and I would like to give a specific shout out to Dr. Benedict Dauer, and also all of our other collaborators with our samples and amazing discussions that led to this amazing work. I also like to thank the WPI-SKCM² for organizing the summer workshop and including me and helping me present my work and funding my travel and staying over here in Japan. And with that, I would like to conclude and I'd be happy to answer any questions you may have. Thank you.
Thank you for this very nice talk, please.